Hello everyone, my name is Alexander Sadovnikov. I'm a researcher at the BioCat pharmaceutical company and a master student at the corporate master's program of the JetBrains and at Mo University Software Engineering. Today I'm going to present my research titled Statistical Potential to Improve Antibody-Antigen Docking. But first, let's take a look at quite distant from the reality, but yet descriptive example of how one can create a drug. Let's suppose that there exists a cancer cell. We know that cancer cells are bad, and so do cells that live in our immune system. For example, these ones, T killers. They have a special hand with the help of which they determine whether some cell is bad or not. If that cell can't shake T killer's hand with a hand of its own, it's bad and should be killed. But to make matters worse, some cancer cells have grown themselves such hands, scientifically called receptors. When T killer comes to the cancer cell that has this receptor, it connects to it and doesn't identify cancer cell as a bad one. But what we as researchers can do in order to prevent this interaction? Well, we can cover cancer cell's receptor with an antibody, for example. It's a molecule that can be produced by our immune system and can relatively easily be produced by humans. And receptors to which antibodies bind are called antigens. So there exists a lot of ways of developing a drug nowadays, one of which is called rational drug design. It's a form of development of drug that uses computer-aided modeling. One of the steps during the rational drug design is the prediction of a conformation of two molecules. It's important because sometimes molecules don't bind to the target where we want them to bind, and other poses are more probable than the ones that bring us the therapeutic effect that we desire. Therefore, we come to the problem of docking. Its formulates as follows. Finding most probable conformation of the two molecules. It's a very challenging task, yet a very interesting one. One of the techniques used to solve this problem is called grid-based docking. Basically, during the grid-based docking, antibody and antigen are placed into three-dimensional grids. Correlation of those grids is calculated, and this correlation reflects shape complementarity of antibody and antigen. And the whole process of grid-based docking looks as follows. First, one needs to scan rotational space of two molecules, then scan translational space of two grids, and choose conformations with maximal grids correlation. And the thing is that this choice can be drastically sped up by an FFT algorithm. That's why grid-based docking techniques are very popular. And in 2006, docking algorithm called Piper was introduced, and it brought something new to the table, something that improved the accuracy of docking algorithms. It brought new correlational terms to the grid-based docking stage. First of all, shape complementarity correlation was replaced with van der Waals energy correlation, and a new term that accounts for the electrostatics interaction was introduced, and both those terms account for physical properties of structures, but that turned out to be not enough in order to conduct an accurate docking. Therefore, Piper introduced a new correlational term that accounts for something called statistical potential, which in its order accounts for the probability that a given structure exists in the real world. And Piper, as of today, still is the most accurate fully automated docking algorithm. But how can one create a statistical potential, and how does it work? Well, statistical potentials are just two-dimensional tables, rows and columns of which are the atoms types, and values in the cells of those tables are just some values calculated by a formula that we'll see later. Let's see how one can evaluate complexes' energy in the given statistical potential. First, we need to iterate through all atom pairs in this complex, where one atom is from the antibody and the other atom is from antigen. For each atom of the antibody, we choose only atoms of the antigen that lay no further than given distance, and we look at every pair and see to which value in the statistical potential table their interaction corresponds. After that, we sum up values for all atom pairs iterated this way, and the resulting double sum is the statistical potential energy of the given complex. Let's look at those magical values that lie in the core of the statistical potentials tables. They are obtained using inverse Boltzmann approach. Its key feature is that it expresses complex's energy via the probability of that complex existence. In our case, complex is just two atoms. For two atoms, a formula to calculate the energy based on the statistics looks like this. where p-ops is the probability of atoms of type I and J interacting at a given distance, and p-ref is the probability of atoms I and J being at the given distance like at all. Piper introduced new statistical potential called DARS, which presented a novel way of calculating p-ref. P-ref usually before the DARS was calculated using some approximations, but DARS introduced new way of doing it by generating artificial set of complexes and gathering that statistics from it. So how can one calculate p-ref like DARS did? First, one needs to generate physically random conformations using Docking algorithm, and then gather the statistics needed to calculate p-ref. Well, of course, DARS has some room for improvement, and that's why the last update of DARS happened in 2012 when DARS statistical potential was introduced in order to improve accuracy of antibody-antigen docking. Second of all, process of DARS gathering hasn't been automated ever since, so whenever one needs to update the statistical potential, he needs to start from scratch. What's worse, DARS doesn't account for distances between atoms, and that seems not very accurate, and there is definitely room for improvement over there. But main takeaway from this slide is that in order to create novel statistical potential, it's better to start from the update of DARS on the new data. At the BioCut we have our own docking algorithm called Hedge. And its main feature is that it heavily utilizes GPUs. But the problem here is that Hedge doesn't yet use statistical potential, and there is hope that its accuracy can be significantly improved by using statistical potentials. And one more thing that I need to tell you before the main part of this presentation is how to benchmark docking algorithms. Well, there exists a protein data bank, a database of all the molecular complexes and structures that are available in the world. And there exists some molecular complexes, but they are alone not enough to benchmark docking algorithm. We also need to find standalone parts of those complexes, and the ideal docking algorithm should turn the standalone parts of those complexes into something very close to the native complex which those parts form. And there exists a dataset containing complexes in their standalone parts. It is called ZLab benchmark dataset, but it has a big problem. It contains only 28 complexes of type antibody-antigen. Its last update took place in 2015, and no tool exists for the automatic updates of this dataset. So there is one thing that we can take away from this slide, is that in order to properly test antibody-antigen docking, more complexes than 28 are needed. And goal of my research was to develop novel statistical potential for antibody-antigen complexes that will improve accuracy of Hedge. A research plan looked as follows. First, we needed to confirm the hypothesis that statistical potential will improve Hedge's accuracy. And second of all, we needed to create antibody-antigen DARS-like statistical potential. And subtask for this were the development of benchmark for comparison of statistical potentials and creation of the potential itself. And the last task that hasn't been finished yet is to add accounting for distances between atoms into develop statistical potential. Well, let's talk about the task of confirming the hypothesis that statistical potentials improve Hedge's accuracy. Plan for it looked as follows. First, we improved Hedge's front end, which is written in Haskell, and Hedge's backend, which is written in C, in order to support statistical potentials at all. After that, we developed a benchmark to compare performance of Hedge on ZLab dataset, and after that we evaluated algorithm's accuracy. It's important to notice that as a statistical potential for this task we chose DARS because we just wanted to prove the hypothesis. Let's see how Hedge's performance is evaluated. Well, we took 128 complexes from ZLab. They are not particularly antibody-antigen complexes, but since we want to just prove the hypothesis, it's okay. Before docking, for each complex we have a native complex and its standalone parts. And after docking we have a range of conformations obtained as the result of the algorithm's work. Those conformations are sorted by the correlation, and conformations with top correlations are usually the result of the whole pipeline. In order to benchmark this, we looked at RMSDs, they are basically distances of complexes produced after docking to the native complex. And the RMSD is just root mean squared distance between corresponding atoms that is measured in angstroms. We calculated RMSDs and looked at different tops of conformations obtained after docking. And we built a heat map, which rows and columns were top ends and RMSD cutoffs. And each complex contributed a 1 to certain cell of the heat map if and only if there exists a conformation in the first n poses obtained after docking with RMSD no more than R to the native complex. And we built those heat maps for version of Hedge that uses DARS and for version of Hedge that doesn't use DARS. Actually, the resulting heat map that you will see is the difference between those heat maps. So every cell in this heat map reflects how much better the version of docking that uses DARS statistical potential is than the version of docking that doesn't use DARS statistical potential. And we see that difference is very drastic, and clearly use of statistical potential improves the accuracy of Hedge for every pair of top N and the RMSD cutoff. Figuring that out, we moved to the next task of creation of antibody-antigen DARS-like statistical potential. And its first subtask, development of benchmark for comparison of statistical potentials. First, we needed to create a data set to run our benchmark on, and since that lab contained not enough structures, we developed our own dataset called ABASE, and it contains 86 complexes of type antibody-antigen, and it has automatic pipeline of its update in order to keep it in a relevant state. As a benchmark itself, we chose technique quite similar to one that we used to compare performances of docking algorithm with two major changes. First of all, when docking standalone parts of native complexes, we used correlation function that doesn't account for statistical potential in order for our benchmark to be unbiased towards any statistical potential. And second of all, we sorted the conformations in the order of their statistical potential energy. Therefore, we created benchmark with two major tweaks that are aimed at reflection the discriminatory power of the statistical potential that is being benchmarked. So the step of creation statistical potential looked like this. We titled our statistical potential CBD's Untitled Statistical Potential, and as the training set, we choose the subdap database that contains all the antibody-antigen complexes present in the PDB. And in order to refine those complexes, we use techniques that we developed during the creation of the ABASE. And as the result of applying them and of the deduplication, we obtained 1200 structures for the training set, which we divided into observed state part and the reference state part randomly. Observed state part and reference state part are used to calculate pure ops and pure ref from the inverse Boltzmann approach formula. Well, for reference state, we generated 5000 conformations for each structure, and after that we gathered some statistics using for the observed state data parallel Haskell algorithm, and for reference state data CUDA-C driven algorithm, because there is just too much data to process and we needed to do it fast. The main takeaway from this slide is that novel statistical potential that we have developed is built on 12 times more data than its predecessor DARS, that also was aimed at prediction of antibody-antigen conformations. Well, let's see how DARS compares to DARS on the ABASE dataset and using our benchmark. Well, quite interestingly, DARS is by far better than DARS on this benchmark. Every cell corresponds to by how much DARS outperforms DARS. And it's an interesting result, especially since DARS was built specifically for the antibody-antigen complexes. Well, let's see how CBD's untitled statistical potential compares to DARS on our dataset. Well, difference is not that drastic, but if we look at the top left corner of the heat map, we see that here the difference is pretty noticeable, and that's cool because this part of the heat map corresponds to lower tops of structures obtained after docking, and usually those tops are moved to the next parts of the docking algorithm's pipeline. So really we created a statistical potential that works better than its analogs at discriminated near-native conformations, but let's see how does hedge perform using this potential compared to the hedge using DARS. We tested performance of hedge on the abase, and the difference is quite impressive. In the majority of cells, hedge that uses newly developed statistical potential outperforms hedge that uses DARS on more than 10% of the validation set. Therefore, we have achieved our goal of improving hedge's accuracy on antibody-antigen complexes. And the summary of this work is that we have created automatically updated benchmark for testing accuracy of docking algorithms and statistical potentials. We have developed novel statistical potential that proved itself to be better than DARS and RDARS on the created benchmark. And what's most important, developed statistical potential improves hedge's accuracy compared to the DARS statistical potential. And for future work, there is left addition of consideration of distances between atoms to the developed statistical potential. Thank you.